Hello boys and girls, welcome to another episode of FoulkesBrau. Today I thought we'd carry on with our Back to Basics series with the humble BJT bipolar junction transistor. In the first part of the series we had a look at how we can use the transistor in the saturated state as a switch. And in the second part of the series we saw how we could use it in the active region as a voltage regulator, and today I thought we'd go back to the saturated state and use it for something far more useful. We're going to take a look at two variations of circuit that I've put down. The second one being an improvement on the first. The circuit is a typical Astable Multivibrator, a big engineering word for the humble flip-flop. So if you ever wanted to make something where you have a light going on and then off, and then another light going on and off, and so on, and flipping and flopping between the two, like our government, you can make a circuit like this. It's not very difficult. A little bit of maths. I will take you through the circuit, through the maths, how it works, and then we'll have a look at some waveforms on the scope. Let's get to the bench. Right, here is the circuit for our Astable Multivibrator. I'm just going to call it the humble flip-flop from now on. Astable Multivibrator is just too much of a mouthful for me today. As you can see, it looks a bit like spaghetti, but it's not that difficult. Forget about the resistor values. What we need to understand, we've looked at how a transistor works. So we know to switch this transistor on, for example, the voltage there must be bigger than the voltage there by about 0.7, 0.8 with the 2N3904. The same for that transistor. So we can see that's tied to ground. So we need 0.8 volt there or 0.8 volt there. Difference to switch either transistor on. Interesting, we've got two electrolytic capacitors in here. Strange, hey? Positive tied to the collector of that transistor, positive tied to the collector of that transistor, and the negatives tied through a resistor to the positive rail, but also crossing across to each one's base. What you can see, I haven't used the transistor as we'd normally do. Output would normally be here. In other words, come out here, just move that LED down and go to ground. Same difference there. How does this work? Well, let's think of it like this. I'm just going to say, for argument's sake, when this is dead, everything is off. The capacitors are discharged in a dead state. There's no voltage in there. We know that capacitors can charge up on their own. The bigger ones normally do. Let us say, when we switch the voltage on, the current is going to flow. It's going to come down to here. That transistor is off. So I'm going to put this piece of paper here. So that part of the circuit is off. The current is also going to flow up to that point. That transistor is off. It's going to come down that leg, and it's going to come down that leg. And let's just say that transistor is off. It's going to come down that leg first. So what is it going to do? It's going to go into that base. We're limiting the current into the base. Remember, we'll get to the calculations, but remember our beta of the transistor. So we're limiting the current into the base, so we get our voltage drop here to switch it on. So that transistor is going to switch on. That capacitor is going to charge. We have a positive voltage on that side, but look at that resistor ratio. 5K6, 5,600 versus 470. So pretty soon this positive is going to be more positive than that. Remember, we've limited this to 0.8 or 0.7. So pretty soon we're going to end up with a whole 12 volts over here. When we do, it's going to overcome that. So that transistor is going to switch off. Are you following me? So then when that transistor switches off, because we've had current flowing through this side, that side is not negative, it's zero. So the current will flow through this way and switch this transistor on. Again, so when this transistor is on, that transistor is off, so this capacitor here on that side is charging. Pretty soon it's going to become more than that, so this transistor will switch off and we'll go through the cycle again. So we'll flip and we'll flop and we'll flip and we'll flop, and by doing that obviously we will switch that LED on, that current path there, and the next cycle we'll switch that current path on there. So we'll flip on, we'll flip on. The important thing to note, when that transistor is on, that capacitor is charging, and vice versa. When that transistor down here is on, C1 is charging. So when Q2 is on, C1 is charging. When Q1 is on, C2 is charging. And that is how this circuit works. Not rocket science, not very difficult. The values, well, let's just move the calc sheet over a little bit. Forget about this up here. What is important, I've said the beta or the gain, because we're using this in saturation. So from episode 1 I told you to assume a beta of 10 or a HFE or a DC gain. So that way we know that this transistor will switch into hard saturation. So if we look at the values for R1, how do we calculate it? Well, R1 and R4 are going to be the same. R1, R4, same value. So we need VCC, which is our 12 volts, which we're supplying it with, minus VCE. We can get that from the data sheet for the 2N3904. It's the volt drop when this transistor is in saturation between the collector and the emitter, 0.3, and minus the VLED. The volt drop on this LED is 3 volts. I just happen to know that they're high white brights. Versus the current, take that all, the sum of that, divided by the current of the LED, the current that we want to feed into the LED, or we said 20 milliamps, so 0.02 amps, will give us 435 amp, well, 435 ohm. We don't have a standard resistor, 435 ohm, so you'll see R1, R4 I've made 470 ohm. It's always better to go up. All that happens is we will bring the current down that is flowing through the LED, which is not a bad thing because 20 milliamps is on the limit. It's basically running flat out. If we bring the current down a little bit, great, we extend the life. Now we look at what current do we want in the base. So we sorted R1 and R4 out. We need to look at the current that is flowing into the base of each transistor. Well, that's pretty easy. What is the current going to flow through the collector? In other words, the current flowing through this collector part, because the current anywhere in this leg is going to be equal. Current flowing through the collector divided by the beta, which we said was 10. So 20 milliamp by 10 divided by 10 will give us 2 milliamp. Simple calculation. So we want to put 2 milliamp to drive 20 milliamp. So to calculate R3, we just say it's VCC minus the base emitter volt drop divided by the current through the base, so it's 12 minus 0.8, divided by 0.02, well, we get 5K6, and 5K6 is a standard resistor. Very simple. So that has got us that. Now the more, how would I put this? So now you're asking me, how do we determine the timing of this? Because if you notice, there's a resistor, there's a capacitor. Hang on, that's an RC circuit, a resistor capacitor circuit, an RC timing circuit. So simply put, tau, I'm not going to derive tau, I'm going to give you an approximation. It's easy enough, and it'll get you in the ballpark. Tau is 0.693 times the capacitance times R1. So our timing constant, 0.693 times the capacitance value times the resistance value, R1 or R4 in our case. So I just put in 470 microfarad, 0.693 times 470 microfarad times 470 ohms, give us 153 milliseconds per timing constant, or per time cycle. But that 0.693 means in one timing constant, the capacitor will charge to 69.3%. The next timing constant, it will charge to 69.3% of what is remaining. The next time cycle, 69.3% of what is remaining, and so on and so forth. So, as a rule of thumb, if you want the actual time till the capacitor is charged, or our timing constant, or our time cycle, take that 153 milliseconds and multiply it by 5. And that will give you one complete cycle. In other words, a full charge, a full discharge. So let's get the circuit, the breadboard out, and let's have a look at it. So here we have our breadboard, our two little transistors down in there, our two capacitors at the back here, our timing resistor, the 470, the 5K6, 5K6 for the second transistor, the 470 current limiting resistor for the LED, the same with that one, current limiting for the LED. That LED common, or cathode, goes to the positive side of the capacitor. From the positive side of the capacitor, it also comes to the first pin of the transistor, the collector. The negative side of the capacitor goes to that resistor up there, that 5K6, excuse me, as well as to the base of that transistor down there. So what I'm going to do, I'm just going to probe the one side. You can see the 3 legs in there, hopefully. There they are. I'm going to probe the left hand side, the left leg, the collector, and I'm going to probe the base. And I just want to show you the wave form. So if you remember, I said that is normally the output of a transistor NPN circuit, NPN transistor circuit. And I'm going to show you why we don't want to use that point there as an output, because typically we're going to be expecting a square wave there, and I think you're already saying, but that capacitor is not going to give us a square wave, and it's also going to affect our drive circuit. So it's all got to do with that capacitor and the capacitance between the collector and the base emitter and the collector emitter. Remember, these are silicone devices, so we will have problems with that, even though it's more pronounced in MOSFETs, but yeah. So let me get you up to the scope. You know where I'm going to probe now. I'm going to probe the collector, the emitter, I've shown you in the circuit, I'm actually the collector and the base, I'm actually probing that point there and the drive point. So let's have a look. Oh, it'd be pretty stupid if I didn't show you what it did. So if we switch it on, you can see the two LEDs are flashing. But what you should notice as well is that the LED is not switching off completely. It switches on and the capacitor is draining. It's on, it's draining, on, it's draining. So it doesn't switch off completely. So it doesn't look, well, unless you like that sort of fade, it doesn't really look that great. Right, here we have a new improved version of the circuit. If you look, these four paths stay exactly the same up to that emitter point. What we've added is an extra leg with our current limiting resistor, our LED, and another transistor. We've done the same on that side. So this emitter is going to drive that base. This emitter is going to drive that base. Why? Well, we now make ourselves isolated from any nonsense going on in this circuitry here. This transistor and this transistor will act independently of the nonsense in here. They will only switch at the right level on and off from that transistor. Same as this one will switch based on that one. So that capacitor charging that we saw, or that off time that we saw with the knee, we won't have that here. We'll have on, off, on, off. Remember, this is a relatively high impedance, high resistance input. Impedance is the engineering term, the same as that one. So although it does take a little bit of current at 2 milliamps, and there is a little bit of gate charge that comes into play here, for the frequency we're switching at, we should get that point there and that point there measuring a relatively stable square wave. The only thing that changes here are R5 and R6. I calculated for 15 milliamp, in this case 12 minus 3, because we don't have that drop across that collector emitter anymore, and I've changed the LED current that I want through. We come out at 600 ohms. Well, the next standard value is 680 ohms. If you do the back calculation, you go back to instead of 15 milliamps, we get 13 milliamp switches. Still very bright on these high brights. So our circuit, let's bring it in. I'll take the autofocus off again. What we can see, we have our original circuit. There's one transistor, there's the other transistor hidden behind this white jumper. So that was Q1, that was Q2, there's Q3 behind that LED, and Q4 behind that LED there. So those are the two extra transistors I've added. Okay, so these two down here. Let's have a look how this one performs. On, off. See? Much sharper. We'll just move it over a little bit for you. So what I'm going to do is I'm going to probe, and you can notice also the brightness is relatively, the intensity is very, it's quite bright. It's not, going down to 13 milliamps, it's not a hell of a difference. So what we're going to do, I will probe that transmitter's collector. This side will be exactly the same, so it doesn't matter which side we work on. And then what I will do is I will set up a probe to show you, I will set up 4 probes to show you basically the relationship between these timing circuits. So if I probe here, for example, and I probe here, for example, and if I probe here and here, well, here I'm seeing the positive side of that capacitor. I'm also seeing what is happening on the collector of the transmitter. Oh, sorry, the transistor. If I probe here, I'm seeing what's happening on the base as well as the negative side, and vice versa. So I'm going to probe here, 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 and here. But first, I'm going to probe, well, actually on that side to show you the square wave. So let's go up to the scope. Right, so as we said, first place I'm going to probe is here, the collector, and compared to the previous waveform, that's what you get. Okay, I've already inverted it. So that's where the collector is on. In other words, it's the LED is on, and that's where it switches off. And you can see it's relatively nice and square. If we zoom out a little bit, sure, we've got a little bit of ringing, a little bit of noise, but that's, for what we're trying to do, I think that's relatively okay. So, yeah, that is the collector, much improved. What we're going to do now is I'm going to probe that point, that point, that point, and that point, so we can see the relationship between what is going on. So let me set that up. It takes a little bit of time. Let me just get my 4 probes in and we'll come back. Right, so the way I've set this up, probe 1 is here and it's inverted. So in other words, it will go high when this is on. Probe 2, channel 2. So this is going to be the yellow trace. This is going to be the cyan trace. Probe 3, which is inverted, which will be pink, and probe 4, which will be blue. So if we look at the scope, let me zoom in a little bit for you. It looks a bit convoluted, but don't worry, we'll explain it now. So let's just get our fix on. So let's look at probe 1, and which is the collective Q1. In other words, it's LED 1. We only want to look at probe 1 and so channel 1 and channel 2. We don't care about channel 3 and 4. So if we take a look at that, we can see what is happening. We are switching our next transistor on. Yes, probe 1 is switching the next transistor on. Remember, it's going through there, through that transistor to there. So that's what we're seeing. It's a lot more square compared to the first signal. Probe 2, we're seeing the base of transistor 1, or the output of capacitor 2. So what we can see, that's the base. It's switching on, off. It charges, it switches on, off. When it switches off, obviously we've got this knee. And the same thing is happening in channel 3 and 4. Exactly the same thing. But let's look at channel 4 versus 2. We'll switch channel 3 off. So we're looking at the base of each alternate transistor. So if I move, let's see, which one have I got? Okay, give me channel 2 and let me move it up. We can see the waveforms look pretty much the same. What is interesting, that is our 0 line there. You can't really see it, but it's about there. So the base is actually going into the negative. You can see that it's actually been pulled hard down. And then it's got a slow charge just before positive. So that small voltage is what our base emitter voltage is, the same up there. That small little bit there. If we look at channel 1 and channel 3, same thing. This one's on, then that one's on. This one's on, that one's on. But they're never on completely together. There's always a gap. So, interesting. Like I said, when Q1 is on, C2 is charging. And we can see that very, very clearly if we look at which 2 would we look at? It's 1 and it is 3. Channel 1 and channel 3. So, yeah, I hope that helped a bit. Very simple circuit. Again, like I say, add the extra transistors in, they cost maybe 20 or 30, not even. If you're buying them single, maybe 20 or 30 cents. But well worth it these days. I mean, we're not driving high current here. And that's very simple. So let's finish up. Well, there you have it, boys and girls. We've come to the end of another episode. Another interesting use of BJTs. If you need a simple oscillator, it can work. You just know that it will drift. It's not going to be the be all and end of all of what you need. The circuit may look a little bit complex. It's actually very, very simple. Just keep your wits about you. Important to understand, capacitors, when you power the circuit on, will be a dead short initially until they start charging up. So don't forget those inrush resistors or current limiting resistors. The calculation's very simple, not difficult maths. Anyway, I hope you learned something. I hope you had fun as always. And until the next one, take care, be safe. Cheers.